Good day, my name is Wynand Lambrechts and I will present to you my doctorate research titled The Modelling of Transceiver Propagation Characteristics through an Analog Silicon Germanium BiCMOS Integrated Circuit, supervised by Professor Saurabh Sinha. I will briefly run through the agenda for this presentation to give an overview of what can be expected during the talk, as well as highlight some important considerations. Firstly, I will provide an introduction to the research in order to summarize the work done and the scope of the proposed study. The mechanisms considered to complete the proposed research will be outlined and presented next. Importantly, to have a clear and concise goal for the research and a measurable outcome, the research hypothesis will be presented and cross-referenced throughout this presentation. The research tools required for simulations are given, and the proposed mathematical and electromagnetic models, electromagnetic simulated results, as well as the electronic circuit results are presented. A layout of the final prototype structure is shown, followed by measured results and a comparison with simulation. Finally, a conclusion is drawn with reference to the research hypothesis, and references are given with possible future work that could emanate from this research. There are several advantages to using extremely high frequencies, millimeter band frequencies ranging from 30 GHz to 300 GHz, with this work focused on 60 GHz. Some of these advantages and applications are given with aid of the figures presented in this slide. Uncompressed multimedia streaming for high bandwidth 3D wireless streaming content is possible. Currently, a usage model of the IEEE 802.15.3c standard are used at this frequency. Limitations such as short transmitting distances can be converted to advantages, as highly directional signals are considered secure with only a 4.7 degree beam width, as signal interception is difficult and less likely. Interorbital communications with large bandwidth and little atmospheric attenuation present give opportunities in space applications. Radio astronomy and remote sensing can determine the temperature in the upper atmosphere through measuring the radiation emitted from oxygen. Proactive meteorological and climate sensing could enable preemptive preparation for possible natural disasters and climate changes. Optical data transmission with matching CMOS circuits can produce a high bandwidth links with limited bottleneck of active components. Systems are able to see through materials and identify possible threats at 77 GHz, such as in airport environment, radar applications, and other high security situations. To contextualize this research, we investigate a common transceiver system as shown in the top of the figure, consisting of a transmitter for this research within the 60 GHz spectrum, and this signal then propagates through a channel with inevitable attenuation before it reaches the receiver antenna. This research proposed to represent such a system on an integrated level, using electronic components to mimic the operation of the signal and provide possibility for real-time analysis through a control variable to change the amount of attenuation experienced with reference to environmental conditions experienced. As to provide a clear summary of the proposed research and the goals to achieve, the research hypothesis can be presented as follows. If an equivalent electrical circuit model of a radiating antenna and a variable filter operating in the millimeter wave spectrum using only passive components can be combined, then it can be used as an analog, real-time, path loss prediction model that eliminates the need to down-convert signals for analysis in the digital domain. Each parameter considered and researched are summarized here, and form an integral part of the models and equations used to construct the mathematical, electromagnetic, and electronic models to represent the millimeter wave signal. Free space losses are considered high-frequency losses, and they are dominant at millimeter wave frequencies and quantified within this research. Oxygen absorption within the 60 GHz band is a dominant factor and therefore also included as a notable attenuation factor. Reflection and diffraction losses as a result of substrate integration are considered, as this millimeter wave antenna is manufactured on a silicon substrate. Rain rate. In this work, research is applied to the South African climate regions and can be adjusted for other geographical areas to allow a more global context. Radiating structures or antenna theory, is adapted for high-frequency complexity that increase when accounting for interrelated attenuation mechanisms that occur in practical environments that can become mathematically cumbersome. IC layout techniques such as the grounding strategies and component symmetry, while adhering to layout rules and minimum lengths, is required. Measurements are interpreted to determine the correlation with simulated results and analyze differences that might occur from external sources of noise and parasitic disturbances. The research tools used to simulate the mechanisms mentioned in the earlier slides are MATLAB, used for mathematical representation of the fundamental equations, CST Microwave Studio to construct and simulate a radiating structure or dipole, and also to export the transfer characteristics to be interpreted and used to construct an equivalent circuit model through an analytical analysis of the information. Finally, Cadence Virtuoso, used to simulate the electronic circuits and perform circuit layouts to be prototyped for measurements. Process Design Kits, or PDKs, from the IBM Foundry has been used for all circuit level simulations. The research questions that had to be asked in order to enforce this research hypothesis and create clear and tangible goals are summarized here. Firstly, how to empirically define path loss prediction models at 60 GHz. Is this method feasible, and will it provide accurate results to define path loss prediction models, and taking into account as many mechanisms present would not increase the mathematical complexity beyond practical limits? The second research question asks if it is possible to derive a method to convert these models into analog IC representations using standard passive components. Can these transfer functions be derived to fit electronic circuit operation? What are the benefits of using only passive components in circuit design where possible, and what are the drawbacks of these, if any? Finally, the question is raised on how to develop an equivalent electronic circuit for a radiating structure at millimeter wave frequencies. Is it possible to accurately present the radiating structure as an equivalent model when substrate effects and high frequency effects have major impact on the transfer characteristics? How does interconnecting these circuits influence performance, and what are the layout strategies to perform deviation from expected results? High-frequency structure mathematical models can become very involved to solve, taking into account all parasitics, and find a way to simplify the models as opposed to trying to solve very large transfer functions is not possible within MATLAB. This was tested, and the computing time and resources required by MATLAB was deemed impractical to solve such an equation. Path losses usually fed from a CPU or a FPGA. This work proposes to build a real-time system-on-chip block to simulate transfer functions. The research also aims to identify building blocks for future add-ons to have a complete system-on-chip integration. Some of the comparative studies that were referenced and used during the formulation of the research hypothesis are shown in this table. This research focuses on methods to determine and measure losses incurred when transmitting at millimeter wave frequencies, with experimental setups of each also given. The information within these articles also provide estimations from experimental results of attenuation through specific materials, as well as attenuation through humans and moving objects. The impact factors in cited half-life, which is defined as the median age of the articles that were cited in the JCR year of the works chosen, are relatively high, with the highest being 3.121 with cited half-life 7.4, and the lowest in this comparative table being 2.063 with cited half-life 4.9. The contribution of each study is highlighted and can be found within this thesis if more information is required. The previous table continues on this page, and this work and its contributions, which are electronic representations, rain rate additions, and electromagnetic simulations, are mentioned explicitly in this slide. This work, published through a peer-reviewed international journal, has contributed to the body of knowledge through its electronic representation of a radiating structure at millimeter wave frequencies, and including substrate parasitic effects. Electromagnetic simulations are provided for antenna propagation as comparisons to the measured electronic circuit representation. This slide shows the mathematical models of the three disciplines used to complete the required simulations and designs to verify the feasibility and accuracy of the research hypothesis and research questions, namely the path loss prediction model, electromagnetic structure simulations, and electronic low-pass filter equations. The first equation is constructed to represent the path losses at millimeter wave frequency, specifically around the 57 to 64 GHz unlicensed band, where constant values are given assuming operation within this band. The equation accounts for free space losses, reflection and diffraction losses, attenuation through material, and rain rate attenuation. The second set of equations are used to construct a dipole antenna to operate in the desired frequency range, and these parameters are verified through EM simulations in CST Microwave Studio. Mathematical derivations to estimate a first-order transfer function for low-pass filters are presented in the third table. These equations are used to determine the appropriate order of the filters that would enable the required attenuation, influencing the addition of noise to the circuit and as well as the physical size. In order to determine an equivalent circuit for the radiating antenna, taking into consideration the high-frequency substrate and parasitic effects, and not considered using first-order equivalent circuits available in the current body of knowledge, an analytical approach was taken to convert the transfer characteristics from a fully operational dipole antenna on a substrate to an equivalent electronic circuit. The resulting transfer function and circuit points at a circuit that is mathematically cumbersome to solve, and this method speeds up the process significantly by estimating a possible circuit where addition of a Monte Carlo analysis can further improve the accuracy of the results. The procedure is iterative, with EM results fed into MATLAB, where the designed script would then use the listed equations and determine the form factor of the results analytically, converting this to the frequency domain analysis of an electronic circuit, and finally determining component values that represent the same circuit behavior. As mentioned in earlier slides, the radiating dipole antenna was designed with CST Microwave Studio. The advantages of designing the dipole as opposed to using mathematical approximations are that all results can be considered as real-world operation, where diffractions and reflections, losses, and other effects not necessarily accounted for by mathematical representations are directly accounted for and included in the electronic circuit that represents the structure. The dipole was designed in an IBM 130 nanometer node geometry with limitations in mind to simplify a physical representation of the dipole and potentially be designed on the same die as on the electronic circuit itself, making measurements and comparisons easily presented. The dipole antenna conductive strips are placed on a silicon substrate, on top of a silicon dioxide passivation layer with thickness governed by the 130 nanometer process as shown. This height above the substrate is 12.02 microns. The addition of the substrate represents a more practical representation of the dipole operation, since without the substrate the antenna would only be suspended in the air. These effects are however noticeable in the antenna operation and need to be accounted for in simulations. The original representation of the Foster canonical form for electrical antennas were then modified to include additional parasitic components expected from the theoretical approach and later verified through simulation results. Inclusion of substrate capacitance and inductance, parallel resonant components, and series resonant components as a result of interconnects and mutual inductance and capacitance from nearby components increases the degrees of freedom, and circuit behavior can be analyzed to verify this operation. The MATLAB script uses results from the EM simulations and populates the component values of such a circuit as a first-order circuit, decreasing the time consumed to mathematically solve the circuit, and further accuracy can be accomplished through the larger degree of freedom as opposed to a general Foster canonical form. The layout of the test circuits on the final 4x4mm die is given here. The layout is part of a multi-project wafer or MPW and the white spaces represent areas where other non-related designs are placed. The left-hand side shows the short open load and through calibration structures, with each test circuit named on the figure. Important considerations in such designs, as a result of high cost and long lead times, are placing each measurable item on the final layout to ensure that measured results can be obtained even if the circuit in its entirety does not operate within specifications. Since passive components are used in the majority of the designs as initially proposed, the circuit could be wafer probed, eliminating the use of external bond wires, which adds parasitic components that require to be accurately modeled and only requiring external connections to low frequency or DC connections. The setup to accommodate the measurements of the prototyped IC is shown. In order to ensure good common ground and minimum interference from surrounding components, a ceramic substrate was gold sputtered, serving as the ground plane, and epoxied onto the surface. The device under test, or DUT, was wire bonded, the required DC and DC ground connections, through a 1000 picofarad decoupling capacitor and onto an external in-house designed PCB, shown in the next slide. The substrate was sputtered at an infrared detector facility, where it was also epoxied and bonded. The measurement probes was characterized and incorporated within the internal matching networks on the die, and the exclusion of wire bonds on high-frequency connections therefore improved expected measured results through elimination of these estimated wire models. The DUT, ceramic substrate, and gold PCB, or printed circuit board, and measurement equipment is shown in this figure. The DUT and decoupling capacitors, as shown in the previous slide, was connected to the external supply through the wire bonds and external wire connections to the ceramic substrate and gold PCB, respectively. Once the setup was completed and measurements could follow, each subsystem had to be measured and compared to proposed simulation results, and any discrepancies that may occur characterized. The results are divided into the following sections. Path losses. These losses are based on the simulation in theory and measured passive filter results used to verify the feasibility of these circuits. Antenna simulations. The simulated antenna results are used to determine the transfer characteristics of the antenna's real-world operation and use the acquired data to formulate the equivalent circuit. The electrical circuits. The result of the electrical circuits designed in schematic and layout using cadence and prototype in a 130 nanometer node. Results are presented and compared to the previous simulations. The passive filters, the filter operation compared to the required path losses are given, and the supporting circuitry such as the buffer and the matching circuits are briefly presented. Comparisons and conclusions. These are required to determine if the research hypothesis was proven, and this is also investigated. These results present the possible, commonly experienced scenarios when transmitting at millimeter wave over short distances. The parameters chosen are a combination of values available in the current body of knowledge, assumptions for common environments, and conditions based on expected conditions within the chosen South African but easily adapted for more global approach climate. The attenuation at small distances from these results suggest expected attenuation of approximately minus 100 dB or 100 dB for the three scenarios, and these results are used to determine the required order and feasibility of a passive low-pass filter to accomplish similar attenuation at millimeter wave. The electromagnetic results of the dipole structure when no substrate is included in the design is given in this figure. These results serve as verification of the design procedure and equations used, as the results of the input impedance, if the absolute value is taken, suggests approximately 73 ohm, whereas theoretically a dipole antenna of half wavelength and 180 degrees separation has an impedance of 73 ohm, therefore verifying that through inclusion of the substrate, the initial design of this dipole is correct. Including the substrate in the dipole design, which is required to serve as a vessel for the metal layer, changes the characteristics of the dipole as expected, and the results can be seen in this figure. In order to correct for these changes, the length, and in some cases the width, of the dipole can be altered to cancel the effects of the added substrate. However, the aim of this study is to determine the effects, quantify it, and represent it with an equivalent model. Therefore, the results as obtained here are kept as is, and the additional components added to the electronic circuit serves to represent these effects, and adding additional degrees of freedom to the design equations for the circuit. It can be noted that the real part of the input impedance at 60 GHz has lowered to 45 ohm, which also suggests that matching this circuit to a 50 ohm as opposed to 73 or 75 ohm would improve the performance of the reflection coefficient, and such results are presented in the thesis. The imaginary component on the current scale is relatively close to 0 ohm at 60 GHz. Through the use of the MATLAB script, importing the data from the previous slides, the following preliminary first-order electronic circuit was obtained, representing the dipole transfer characteristics without a substrate. The results suggest that the circuit does in fact have similar frequency operation compared to the dipole itself, and the changes in the real and imaginary impedance could suggest that the chosen node, which is 130 nanometer component values, could be a limitation of constructing an exact representation of the dipole performance, since these values, the local minima and maxima, are dependent on the possible component ratios of inductance and capacitance obtainable in this technology. The improved circuit with additional parameters to increase the degrees of freedom and enable higher inductances and inductance and capacitance ratios will be presented later in this discussion. These results of the simulated low-pass 7th order filter suggest that through using the component values of the 130 nanometer node, the maximum obtainable attenuation, while still exhibiting low-pass filter characteristics with a minus 20 dB per decade characteristics, in the region of minus 60 decibels, as opposed to the required minus 100 dB as proposed with the path loss function presented earlier. The measurement results of these circuits are also presented shortly to confirm the operation within the required band. Only the Butterworth and Chebyshev filters were prototyped as a result of physical space constraint when designing for an MPW run. These simulation results show that it is possible to change the attenuation in a passive circuit through a DC-controlled active component, which is a common-base transistor amplifier keeping optimal gain bandwidth product. The amount of change is approximately 6 to 8 dB in simulations, where measured results have different limitations, such as parasitic, equipment, and layout constraints, and will become evident in the presented measurement results. The effects of the matching circuit operates as required and designed, where it can be noted from the results in this figure that the real and imaginary impedance of the output at 60 GHz are in fact 50 and 0 ohm respectively. The buffer circuit also assists, without changing the transfer characteristics at the frequency of importance, that no external loading occurs when measurements are conducted. This slide presents the noted shifts of the S11 reflection coefficient when comparing simulations and measurements and the adjusted values, where the modified or improved circuit of the Foster canonical form are used to determine the cause of the shift in this resonant frequency, where such an investigation could then suggest where and how these shifts occur and what is responsible for the changes. The results confirmed that changes in inductance values occurred, large with respect to the changes in the capacitance values, which could be assumed reasonable error between simulated and real-world parasitic parameters within the circuits as a result of the ground plane acting as an inductor due to its geometry, and comparing this theory with the values obtained in the adjusted circuit, which suggested enlarged inductance values, was consistent. The results presented in this slide can be interpreted similarly to the previously shown slide. The operation of the dipole depends on the behavior with respect to frequency and shifts within the frequency domain predominantly and thus presents similar as expected results as with the reflection coefficients. The results for the Butterworth filter are presented in this slide, where although the results near 60 GHz are noisy from upconverting the signal and used with the optimal 67 GHz probe, the attenuation within the 60 dB is within the minus 60 dB range as expected from the simulation results. The micrographs of some of the design circuit structures are presented in this slide. The top left figure is the initial Foster canonical form dipole equivalent circuit, where dimensions of the circuit are visible on the figure itself. The figure at the bottom left displays the circuit with additional components added to the layout to account for parasitic and substrate effects, and the presence of the two white pads at the bottom of the circuit as biasing structures for the buffer circuits to avoid external loading of the circuit when probed. The figure on the right hand side is a Butterworth filter, and the presence of the two white pads at the bottom of the circuits act as biasing structures for the buffer circuits to avoid external loading when the circuit is probed. The conclusions drawn from this research and the results provided can be summarized as presented in this slide. Firstly, research into millimeter wave applications have received priority in recent years due to its potentially large bandwidth application within an unlicensed band, and frequency device operations suffer from losses and noise that are not necessarily characterized in lower frequency applications. Therefore, encouragement to highlight these effects builds confidence in future inevitable applications. The work aims to eliminate the need to downconvert these high frequency signals, reintroducing its dependence on mathematical and computational assumptions, and find a method to exclude these and improve accuracy and confidence in results. Studies into improving antenna models are done in order to increase the accuracy as mentioned. Scripted software is presented to determine a first-order equivalent circuit component values that decrease the complexity and computational time of solving transfer functions that can become complex and possibly impractical. Passive structures as components in the circuits are prioritized to maximize bandwidth capability, where the GBP or the gain bandwidth product of active devices incur limitations within the chosen technology node. Measurements from previous experience were optimized to also, through the use of passive components, eliminate the requirement for bond wires on high frequency connections, therefore eliminating the uncertainty and required characterization of the bonds, especially since machine bonding was not an option and hand bonded wires do have a large tolerance in profiles. These are the journal publications that emanated from this research. Now, future work that emanates from the proposed research can be summarized as follows. Improvements on IC layout strategies are encouraged, and additional test structures to fully characterize all circuit components can be added to such circuit blocks. Thicker ground planes, next slide shows the picture of the current plane, enlarged and highlighted, would ensure less parasitic inductance and accurate results. Path losses from moving objects can be investigated. Phase behavior of the equivalent circuit can be investigated, and the prototype antenna is possible. It's possible to prototype the antenna, and behavior studies is a large field in the current body of knowledge, where isolated analysis on the antenna structure itself can be beneficial to determine further possible parasitic effects. Advantages in characterizing and better component behavior estimations can be achieved through isolating passive components and studying each component individually. As mentioned earlier, the improvements in the ground plane strategy for this work can avoid additional inductances. The figure shows the ground planes as it was designed in this research. Thicker ground planes could eliminate these inductances. The references that play a significant role in construction of this presentation are presented, and a full list of journal publications, conference proceedings, and textbooks that were consulted are available within the thesis itself. This concludes this presentation. Thank you for your time.